The permanent of the random matrix with vanishing mean.
But this is not correct.
Maybe you should throw it.
Yeah. Oh. All right, thanks for coming to this talk. So I'm going to talk about my recent work with Lior Eldar. Here's the archive number, and so the title is Approximating the Permanent of a Random Matrix with Vanishing Mean. So before starting, I'll give you a very quick overview of the outline of the talk. So at the beginning, I'm going to express the main question, which is related to the complexity of the permanent in a particular setting. And I'm going to tell you why we should care about this particular setting. And the main motivation comes from quantum supremacy experiments and understanding the advantage of quantum computers over classical ones. After that, I'm going to tell you what previous bounds we know about the complexity of the permanence related to the particular setting that we consider, and then I'm going to explain our results. At the end, I'm going to go over the proof techniques, which is based on zeros of random polynomials, and the interpolation method that we have been talking about throughout this workshop. Okay, so what is the permanent polynomial? If we know the determinant, it is easy to understand it. If you have a complex matrix of size n times n, then permanent is like the determinant, except that we don't have this sign factor here. So it sums over all permutations of an n-element set and multiplies the element in each entry selected according to that permutation. For example, for a 2 by 2 matrix, the permanent is multiplication of these two elements, A11, A22, plus A12, A21. And the difference between the determinant is this negative sign. So even though they're so similar, we know that determinant is computable in polynomial time, but permanent has very interesting complexity behavior. So it is hard to compute for most cases that we know. The main question that this talk focuses on is to understand the complexity of the permanent in a setting where we consider approximation and average keys. So we can think of computing a function exactly or approximately, or we can think of computing a function for all instances, or like for most instances, which we term as average case. So this talk is about the particular case when we combine approximation and randomness, approximation and average case. So why should we care about this setting? Well, it's an interesting question, and it is related to well-known properties of the permanent, for example, random self-reducibility and so on, which I'm going to talk in more detail in a bit. But the main motivation that I'm going to attract the attention is the quantum advantage, that I'm going to explain what is the main open question that we are trying to understand and resolve, and how does this question relate to this, the interpolation technique and roots of polynomials and so on. Okay, so in recent years, in an ongoing research, we are trying to show that even though the full functioning quantum computer is out of reach, we can prove, we want to show that even weak computers, quantum computers that are too small and very weak in their functionality can still do computations that classical computers cannot do. So one particular example of such a model is known as Boson sampling, which I'm going to explain to you using a very simple classical setup. So consider the setting that you have balls and bins. So you have bin number 1 here, bin number 2 here, and consider that like you have one ball per each of those bins, and the balls are indistinguishable. And I want to look at and at each bin I have I consider the probabilistic process that I move the ball, let's say at the first bin and move it to the second bin. I do it with probability P12 or keep it in the same bin with probability P11, and the same for the second bin. And I'm interested in the events that like I start with one ball in each bin and I end up with one ball in each bin. So it turns out that, well, there are 4 possibilities at the end of this process. I can have 2 balls in the first bin or 2 balls in the second bin, or one ball in each of those. But the setting that is depicted in this picture, the probability is going to be the permanent of this matrix P, which basically encodes the probability of transitions between bins. So that is basically how the permanent gets encoded into a very simple model that, like, you can think of it as a model of computation. And I can generalize this model to more balls and bins. And let's say I have more bins than balls, and I have m balls located in the first m bins. And I'm again interested in the event that I end up with m balls in the first m bins. And I'm again interested in the probability of this event. I denote the P to be the probability matrix whose entry ij is the probability of moving a ball at bin I to the bin j. So it turns out that the probability of this event now is going to be the permanent of the top m by m submatrix of P. So I have a classical model that encodes in its probabilities an interesting computational problem. Even though this doesn't mean that the model can compute the permanent, but let's for now ask that how hard is it to approximate the probabilities of the events coming out of this model of computation. So based on a very non-trivial result of Jerome, Sinclair, and Vigoda, we know that if you have a matrix that doesn't have negative numbers in it, then we can approximate the value of the permanent of such matrix in randomized polynomial time. So namely, we have an FP-RAS. And in this case, since this matrix P is a stochastic one and doesn't have negative numbers, it turns out that actually the permanence and the probability of transitions for this model is feasible, is tractable. Okay, so now I want to add some quantumness to it. I'm not going through the physics, but the quantum model, the Boson Sampling model, which was introduced by Aaronson Arkhipov in this line of quantum supremacy experiments, and they were trying to argue that like this model, even though it doesn't capture a universal, a full functioning quantum computer, cannot be sampled using a classical computers unless surprising statements hold in complexity theory. So the Boson sampling is like, again, the balls and bins model. Instead of balls, now I have identical photons. And instead of bins, I have optical modes. They're the same things. And instead of the probabilistic transition of these balls between modes, I have a linear optical network, whatever that means, that induces some evolution in the model. So the model is that I pass through photons here, and at the end, I sample a certain configuration out of this. So I can think of this again, having one photon in each optical mode and ending up with one photon in each optical mode. Because we have quantum mechanics instead of stochastic matrices, the evolution is governed by unitary matrices, which are like complex generalizations of orthogonal matrices. And it turns out that using simple and like similar arguments, that the probability of, let's say, the event that I start with one photon in each optical mode and ending up with one photon in each optical mode, the probability is going to be now the permanence of a unitary matrix. And related to the permanence of a unitary matrix, and in particular, it is absolute permanence of the unitary matrix squared. And if I have less photons than optical modes, then I'm going to get the permanence of submatrices of a unitary matrix. So now, what is relevant about this model to understand is that I have a model that I can prepare an arbitrary unitary matrix of, let's say, size n times n, and this model encodes in its probability of transitions, encodes the permanent of submatrices of this unitary matrix. So now I ask the same question again. How hard is it to approximate the probability of the events coming out of this quantum computer? Yes?
It's not exactly what they're after.
Well, if I understand the complexity of this,
I think they're after having classical generator of that distribution.
exactly.
Not
Exactly.
It's not
So understanding this question can lead to statements about sampling. So if I know that the approximation of the probabilities for this model is sharply hard, for example, then I can argue that the existence of a classical computer can sample from this distribution implies that
Not exactly, because that your classical example, that distribution, even though exactly compute probability is sharply hard, to simulate the distribution is easy.
Yes, I mean the model is just classical.
Simulate the distribution is easy, but to compute probability exactly is hard.
But that is because the probability of that event was feasible in randomized polynomial time. But if we show that the probability is actually not computable, cannot be approximated in the classical polynomial time, then that means a classical computer sampling from this distribution implies that within the so-called polynomial hierarchy you can approximate these computational problems, which is that is basically what they do, and argue that quantum advantage comes from this model. Does it make sense?
It's more complicated. But then
okay, yeah, we can talk offline. Thank you. Okay, so again, like this is not the computational model that this model performs. That's Leonid said the model is basically a sampling one. But for now, I'm considering just the complexity of the probability that is encoded in this model. And it turns out that now, like the approximation of the permanent is sharply hard in the worst case. And this was shown by Aaronson and Arkhipov. And now what is different here is that we have negative numbers in the entries of these matrices. So that is basically where, so like intuitively, if you understand where quantum advantage is coming to the play, and is basically having negative numbers, like summing terms that interfere with each other and cancel out. So I'm going to say just a very few words about like how this quantum supremacy setting is. Again, so as we discussed, like the goal is to show that sampling from these boson computers is hard for a classical computer. And in their work, Aaronson and Arkhipov in 2010 showed that if there is a classical computer that can sample exactly from the outputs of these boson computers, then we have surprising statements in complexity theory, namely that the polynomial hierarchy collapses, which is the conjecture to be false, like and is a generalization of P versus NP conjecture. So now we can ask, but have we established quantum supremacy? The answer is no, because even a quantum computer cannot sample exactly from its output distribution. And because we have noise, we have experimental error, and so on. So the relevant question is, how hard is it for a classical computer to sample approximately from the output of such quantum computer? And a good toy model for approximate sampling is total variation distance. In a work, Aaronson and Arkhipov add two conjectures to the picture, and one of them is exactly the question that I asked at the beginning of the talk. That how hard is it to approximate the permanence of a Gaussian matrix with high probability? And the Gaussian matrices come into the picture because the submatrices of random unitary matrices are close to Gaussian. So they come up with a clean statement of a conjecture, and we hope to find the answer. Okay, so now I'm going to explain to you the previous bounds that we know about the hardness of the permanent in this particular setting, and tell you what final result, what do we add to the picture. So first, even though permanent is sum of n factorial terms, by a formula by Reiser, we know how to compute it in exponential time. And we haven't been able to improve on that, like for the worst case instances, for exact computation, only by saving some constant factors. We can ask the question that how can we actually do better? Can we compute the permanent in polynomial time? In a seminal work in '79, Valiant showed that probably the answer is no, because for a 0-1 matrix, the permanent is sharply hard to compute exactly. And as I mentioned, so we can ask, like, how about approximation? So that is the picture for the exact computation. What can we say about approximation? Jerome, Sinclair, and Vigoda in 2004 showed that if you have non-negative entries, then you will have FPRAS, fully polynomial randomized approximation scheme, fully polynomial time randomized approximation scheme. So again, we ask the question that what is the complexity of approximation not having this constraint, like namely that like you can have negative numbers. We can show that like even approximation is hard. A proof of this was appeared in the paper by Aaronson Arkhipov, but probably it was known before that. And very recently, like the topic of this workshop, we have been able, like by the results of Barvinok, we have been able to approximate the permanent for particular instances of matrices that can have negative or complex numbers, which I just call it, let's say, mild interference, or like which we have been talking about throughout this workshop. Okay, so all of these results were about the complexity of the permanent in the worst case. Now, what can we say about the average case complexity of the permanent? So in a series of work, the last of which being by Kai and others from '99, it was shown that the permanent is hard to compute on average. So in particular, if you consider a finite field of large enough prime order, then if you have a black box that can compute the permanent exactly for, let's say, 1/n fraction of such matrices, yes?
Should also mention this independently also due to Madhu and
yeah, so they use the least decoding by Madhu Sudan that
no, actually,
yeah, so Madhu comes before that. So I think there are 4 sequence of works that lead to that.
No, they're independent.
Okay. Yeah, thanks for pointing this out.
Should mention.
Sure. Okay. Yeah, so it's like the permanent is hard for even to be computed for 1/poly fraction of matrices over a finite field. So this observation was the main reason that Aaronson and Arkhipov used this boson model of quantum computer, because they knew that permanent appears there, and permanent has this random self-reducibility property. So they were hoping to get some robust complexity that, like, when you implement these in an experiment, you would hope that like you would get a distribution over instances that is actually hard to compute. So what they showed was they studied the complexity of this zero-mean Gaussian matrices, and they were able to show that on average it is hard to compute these matrices, the permanent, exactly. But that didn't solve their problem, and as I said, the main open question in the field is to understand the setting where average case and approximation are combined. Okay, so having this background, I think I'm ready to explain the main result that we show. So we show that if you have a Gaussian matrix, the ensemble of Gaussian matrices, with non-zero mean but vanishing, as n, the size of the matrix, goes to infinity, the mean goes to 0, then still the exact computation is sharply hard. Well, this comes from the proof techniques that existed before, but the main thing is that now when I combine approximation and an average case, the approximation becomes feasible in quasi-polynomial time. So we give a natural example of a computational problem that it is hard to compute exactly an average, but only when approximation and average case are combined, the problem becomes easy. So that counters the intuition that having this result will imply that this box is also sharply hard. So, so let me zoom into the results that we are dealing with, the complexity bounds that we want to understand. So this chart studies worst case versus average case, exact versus approximation. So for a Gaussian with zero mean and variance 1. So in the worst case, exact computation includes 0, 1 matrices, is sharply hard, even approximation is sharply hard because you can have negative numbers. And the result of Aaronson and Arkhipov, average case exact is hard. Now the last box is where we are interested in, where we can have applications where quantum supremacy is based on. And our result, in more detail, is that we fill out this chart. First, we show that this chart still remains, this box still remains sharply hard. And if you have the ensemble of Gaussian matrices with mean 1 over poly log log n, doubly log in the size of the matrix, then you'll get a quasi-polynomial time approximation algorithm. And if you further increase the mean value to 1 over poly log n, then you will get sub-exponential time algorithm. So to recap, here is the hardness landscape for the permanent with respect to the mean of the ensemble. So if the mean is 0, it's conjectured to be hard to approximate. Like if the mean value is, so there should be a threshold for the mean that like the hardness is the same as 0 mean. It turns out that like if the mean is like 1 over a square root of n divided by some large enough constant, then the values are within multiplicative value factors of each other. So like here you will have this conjecture to be hard. If you increase the mean to 1 over poly log n, you will get sub-exponential time algorithm. And if you increase the mean by 1 over poly log log n, you will get quasi-polynomial time algorithm. So these were the main results of this work. And if you increase the mean to square root of log n, well, I'm not sure how interesting this ensemble is, but like all entries become positive with high probability, then using results of Jerem, Sinclair, and Vigoda, you'll get randomized polynomial time. So as you go from left to right, the problem becomes easier and easier. Okay, so now I'm going to sketch the proof, and the proof is based on the interpolation technique that we have been talking about. Okay, so let me briefly just go over the machinery of the interpolation method, which was introduced by Barvinok. And so we have, let's say I want to compute the permanence of a matrix A. I consider a univariate polynomial, g of z being permanence of 1 minus z times j. J is the all ones matrix, plus z times A. A is the matrix that I want to compute the permanence for. And at z equals 0, I have just the matrix J, the permanent of J. So the value is just n factorial. At z equals 1, I have the permanent of A. And somehow I want to interpolate from left to right. So throughout, I'm going to denote f to be the logarithm of the polynomial g. Okay, so how do we deal with this? So let's consider this algorithm that I just Taylor expand the log of the permanent. If I compute it at 0.1, then exponentiation gives me the value of the permanent. And so I sum over, let's say, m terms, and I will obtain some additive error epsilon, and then I exponentiate. So additive error epsilon becomes multiplicative error epsilon. So now, like any other algorithm, we can think about running time and correctness. And it turns out that if I need up to n derivatives here, n terms in the Taylor expansion, then the running time is n to the power order n, because the lth derivative is computable to in time n to the power order l. And so, for example, if I get m equals log n, then I get quasi-polynomial time. Now, for the correctness, as we have been discussing, that if it turns, it's related to the roots of this univariate polynomial. If they are all outside of the unit circle with some significant margin, then I will get. So it turns out that like log n many terms in this Taylor expansion is enough. But if I have only one root inside this unit circle, then the error blows up very quickly. So what I want is to push all of the roots outside. Okay. Okay, so there are two primary challenges. First, to understand something about the location of roots. And second, like knowing something about these roots, how can we detour around them and approximate the value? Okay, so in our method, instead of like considering the permanent of 1 minus z times j plus za, we consider the permanent of j plus z times a. And the reason that we do this is just for convenience. So if you sample A to be an n times n Gaussian matrix with mean 0 and variance 1, and if I divide this polynomial by z to the n, then I will get the permanent of a matrix that the matrix is such that as if I've sampled it from a Gaussian distribution with mean 1 over z and variance 1. So now I start with at point 0. I know how to compute the permanent and its derivatives at point 0. Now I go as far as I can. So the larger I increase z, the smaller mean that I get here. So, and I hope that I can do this for a large enough z so that the bound I obtain would be for a small mean matrix. Okay, so the main technical contribution that we make in order to understand the roots is to find a way to bound the number of roots of a polynomial on average. So basically, we do an average case. We find an average case bound for the number of roots of a polynomial inside a certain disk. And the worst case, like these roots can be anywhere, but we show that if you denote n sub r to be the number of roots of this polynomial gz inside a disk of radius r in the complex plane, then in expectation value n sub r is order r squared. Okay, so the goal is to do this polynomial interpolation and go as far as I can. And suppose that I want to compute the permanent for a matrix whose mean value is a very small constant. Let's say it's 10 to the power minus 12. So a very small constant. So this bound tells me that with high probability, so I want to choose the r to be 10 to the power 12. And this bound tells me that like with high probability, number of roots inside this disk is going to be 10 to the power 24. It is large and not feasible on a classical computer that like we can actually, on a laptop computer, but it is still a constant in the asymptotic limit. The main importance is that this bound doesn't depend on n, the size of the matrix. So let me tell you very quickly about how we show this. So the proof is based on a well-known formula in complex analysis known as the Jensen's formula. And we do we find a bound, like in an average case, we find an average case version of the Jensen's formula. So what is Jensen's formula? Consider, let's say you have a polynomial that is not zero at the origin, and if I integrate the polynomial, this value log of g of r e to the power theta, so log of g at absolute g at these the points on this circle divided by the g at point 0, then taking this integration is equal to sum over all the roots inside this disk. So that this bound depends only on the roots that are inside this disk, of log of r divided by the modulus of the root. So using a little bit of work and taking the expectation and so on, we can show that the expectation value of this number and r is going to be a constant times log of the second moment of this polynomial normalized by the value at point 0.
Jensen's inequality, right?
Yeah, this is Jensen's
formula and then Jensen's inequality.
Yeah, for Jensen's formula and Jensen's inequality, exactly. So this inequality
it's the same
comes from,
right?
yeah, the same person. Helps us a lot. Cool. Okay, so, and we can do this because at point z equals 0, the permanent is just not permanent of j, and like the value is not 0. So we can use this, and since this is a constant, all we need to do is to compute the second moment of the permanent of a matrix with non-zero mean. Okay, so now the second task is to convert this observation into an algorithm. So how do we do this? So with high probability, we know that, so let's say this is 0 and this is a large constant, and we know that there are constantly many roots on the way. And we consider a lot of curves that attach point 0 to point r. And we consider a fattening around each of these curves. So if the number of these curves are large and the width of these tubes around these curves is small enough, then by a simple counting argument, we can say that most of these curves should be root-free. So that means that taking a random curve should be root-free with high probability. And just a technicality is that it's important that I don't have a root very close to the origin or a root very close to the final point. So along with showing the constant bound on the number of roots, we show that there is a safe disk around point 0 and a safe disk around point r. And having that, like using this counting argument, we can have faith that taking one of these curves at random, it won't have a root around it with a significant margin. Okay, so now let's say this curve, well, we have sampled and we have faith that it is root-free. What can we do? Well, we can simply just consider a sequence of curves that the function is analytic inside, and we go from left to right. So this is just for the intuition, because, so for example, like if I have sequence of overlapping disks, then I compute a lot of derivatives at point 0, and then use those to compute a lot of derivatives at the first point, at the center of the first circle, and continue all the way here. And at each point, I discard a fraction of these derivatives and do the analysis and show that, like, for the particular regime of the mean value and so on, the error converges. So this is for the intuitive version. There is maybe a cleaner way to do this that I just mentioned it quickly. That, like, if you have, let's say, a root-free strip, like instead of a disk, then based on a result of Marvinok that, at the same time that he introduced the interpolation technique, that,
Come on.
yeah,
Not at the same time.
Oh, it was.
No, come on.
Oh, the
One
book.
of you was at my talk at MIT, right?
Oh, it wasn't.
Where I explained this.
Okay. Okay, so maybe very close to each other.
Okay.
Okay, so there is a polynomial of low degree that maps a unit disk onto this strip, like, or inside this strip. And so let's say if the width of this strip is a constant, and then I would get, let's say, the constant parameter beta, which like implies that I need, let's say, log many derivatives, and all we add to this is to compose it further with the analytic function to go to the curve that we are interested in. So that is basically just a minimal technicality that how to do this in an algorithmic version. Okay, so I want to point out two open questions. Well, the first one is basically the complexity of the approximating the permanent with zero mean and variance 1. Well, what can we say about this? So let me tell you what we believe should be true. Using some numerics, we witnessed that if I consider this random polynomial, like g of a being permanent of z, 1 minus z times j plus z times a. So now the same original interpolation. Now the roots of this polynomial cluster very tightly around a circle, or like something like a circle, around z equals 1. So in a way, z equals 1 is protected by an armor of roots. So that means like I may not hope to interpolate all the way here. And using some heuristics on conjectured anti-concentration bounds on the value of the permanent, or like the bounds, the value of the permanent in expectation and so on, we believe that the radius of this circle should be somewhere around 1 over square root of n. So that means that if this is true, if we can show this, let's say that there are no roots outside of this circle, then that means the best mean value that we can hope for is going to be somewhere around 1 over square root of n, like some constant times 1 over square root of n. And the bound would be sub-exponential time x of square root of n. And like as I said, like mean value 1 over square root of n, like divided by some large enough constant, is as hard as the mean value 0. So the other thing that I want to point out is, what can I say having this promise that the roots are in a unit circle? Like, can we come up with a clever algorithmic technique having this promise, or like to maybe we are able to disprove the conjecture? And another thing we can ask is that, for example, like let's say if you have an NP oracle that can actually tell you that like these are the location of roots, can you verify this? And like, for example, having this promise on being roots on a unit circle, and basically remove these roots and interpolate all the way here, or something like that. The second open question I want to mention is that what can we say about the statistical properties of a random polynomial using this interpolation technique? So we believe that like these techniques are algorithmic, but can we use those in order to say something about random matrix theory, or theory of random polynomials? So the second conjecture in the Boson sampling paradigm is known as the anti-concentration conjecture, which basically says that the probability that the absolute value of the permanent is greater than a square root of n factorial by some polynomial in n, when A is sampled from a Gaussian matrix, is high. And the square root of n factorial is the expectation value. So expectation value of the permanent squared is n factorial. So like the expectation is around the square root of n factorial for the absolute permanent. So now the question we ask is, can we show this at least for non-zero mean permanence? And So for example, around any point, the deviation of the permanent is at least the square standard deviation divided by some polynomial. So I just want to mention two observations which don't lead to a proof, but can we actually use this observation to say use it elsewhere? So the first observation is the machinery of this work, which basically shows that for mean value 1 over poly log log n, then we can approximate the log of the permanent using a low degree polynomial in complex Gaussian variables. The second observation is the result of Kerbery and Wright from 2001 that shows that actually we know anti-concentration bounds for low degree polynomials in Gaussian variables. So can we somehow combine these two to prove some sort of anti-concentration bound for a random permanent? So unfortunately, so D here is the degree of the polynomial, and the anti-concentration probability that we get is 1 minus D to the times epsilon, the deviation here, the power 1 over D. Unfortunately, this is not sharp enough to give us any interesting bounds on the anti-concentration, but maybe if we can sharpen this bound for the particular case of the permanent that we have, maybe we get some results. Or can we use this interpolation? Like maybe when we don't know actually how to do this algorithmically, but like knowing that there is a low degree interpolation, can we say something about statistical properties of random polynomials? Right, that is the references, and that's all I wanted to say. Thank you.
Questions? Remarks, perhaps?
Suggestions.
Suggestions?
So, but I still don't understand one thing. Maybe you can enlighten me.
Sure.
So, the fact that Jerome figured that result absolutely has nothing to do with the fact that you can simulate the distribution. That was known for ages. Okay.
Right.
Okay.
Right.
So I don't. So even if I know how to simulate the distribution, it does not mean that I can have a relative approximation for those probabilities.
That is true. If you have
Not necessarily. It might mean.
yeah. So if you have if you have a randomized algorithm to sample, that is the setting you're interested, then I can do the approximation within the polynomial hierarchy, within the third level of the polynomial hierarchy. But that is correct. That doesn't mean that I have efficient algorithm. But the way we reason about it is the other way, that there is actually a much stronger than third level of polynomial hierarchy algorithm that can approximate these values for the classical version of this model. But you're right, that doesn't imply... it's because
again, even like on the intuitive level, that they did not use that fact, okay, so maybe it even implies, but this was not how they got
No, that's just for the intuition. They did not use the fact. They just wanted to give the intuition that like these negative numbers are what make
one more question, your hardness results. Is it all based on the fact that it's difficult to check whether permanent is zero or not?
Maybe you can do it that way too, but it is basically...
Because again, you do relative approximation.
Yeah.
So in order to do relative, if you can do relative approximation, you at least can distinguish between zero and non-zero.
Yes, but the hardness result is for exact computation on average.
Yeah, so it's more, okay, so the non-average is just, worst case is just if you can, it's known, the permanent, to check whether it's zero or not, it's hard.
Yeah, right.
So what is the idea for that your hardness
exact?
Proof? For average hardness proof.
For average case, exact computation hardness. Yeah, so it's basically like assuming that you have an oracle that that tells you the answer correctly some of the times. Then we sample a bunch of these permanents for let's say the g of z at different points, and we sampled a lot of those, and using the least decoding and like these techniques, we say that okay, so there's a way to recover this polynomial, then we interpolate at z equals the point that I want, and then I do the approximation. But it is basically immediate from the stuff that was done before.
Oh, yeah, nice.
So there are similar conjectures for this class called IQP. So they have conjecture about average hardness for evaluating Ising model with random complex weights.
Sure.
Like that, would your algorithms also apply in that setting?
I try to reproduce the same result there. So there, let's say you have a partition function, you want to interpolate all the way to beta equals 1 or something like that. The best heuristic bound I could find is like beta equals 1 over square root of n, which I don't think if it is interesting. I mean, if I could show like 1 minus 1 over little o1 or something like that, that would be interesting.
Is that the Sherrington-Kirkpatrick model you're referring to? Or?
So I think their conjecture is about you have a complete graph and each edge is a
Gaussian, right?
no, it's a
I think it's
unity.
discrete.
Like eighth root of unity.
Ah.
A random one.
The Gaussian case, Gamarnik has hardness.
Sure.
Sherrington-Kirkpatrick partition.
Okay, so other questions or concerns? Okay, so let us thank the speaker again.